What's going on, everybody? Mr. Diamond, and here we are going to be going over the next category of isomers. The first one was definitely the easiest. Constitutional isomers are really not that bad. It's literally just counting and identifying the chemical formula for them to really identify them. The second category gets a little bit more unique. Now, one key thing to note here before I move forward is that these have to be put together in a different order. Stereoisomers are when they are actually attached in the same order, but their 3D position in space is different. And that might seem a little bit weird, so we'll give you an example here in a minute. But stereoisomers are a lot more complex to identify than just by looking at structures than, say, functional groups. If you look at a picture, you can go, that's an alcohol group, that's a ketone, that's a carboxylic acid, that's an ether, that's an ester, etc., etc. You can just identify them. So we're going to first talk about what makes things stereoisomers and then what groups or structures should make them appear. We'll also be getting into the more complicated versions of this next chapter, but we're going to start with the easiest one for this chapter. The first thing to look for is carbon-carbon double bonds. So a carbon double bonded to another carbon. That pi bond, just like our example from earlier, if I go over here, that pi bond is preventing them from bending, and it's preventing them from rotating to make the two versions the same. So they can't be superimposed, which means I cannot position them so that they completely overlap with each other. It is impossible to superimpose these over one another. Even if I try rotating them, it's not gonna do anything. So we have two naming conventions for them. One that's easier, but can be not allowed to be used depending on the situation. And then one that's more complex, but will always work. The first way to identify or to word these geometric isomers is through Cis-Trans isomerism. Cis-Trans refers to the side of the double bond that the molecule has entered into and continues out of. So for example, in this one right here, the molecule goes down, up, down, and then it's entering, if I hold up my double bond, so here's my double bond here. If I hold it vertically, it enters on the left side and it exits on the right. So it's exiting on the opposite side of the double bond, so that is trans. It's transferring to the other side of the molecule. And then cis isomers, or cis isomers, if I hold it straight up and down, so there's my double bond, notice it is on the same side. It's entering from the left and it's exiting to the left. So this would be an cis isomer, and this would be a trans isomer. So in the pictures below down here, it's entering from, if you kind of think of it vertically, it's coming in from the left side of the double bond and it's exiting the right. So that would be a trans. And this one is, if it's entering from the left side of it and it's exiting the left side of it, that would be a cis double bond. So question could be draw and label both possible isomers of pent-2-ene. I'll work out that example in kind of a later video or in another video. Now, let's make things a little bit more complicated. What if instead of it just being a double bond, what if there was actually things attached to it, like in here? Our rules told us to name based on which side of the molecule the chain continues out of, but in this case, there's chain, or there is stuff on both sides of it. So looking at this, you might go, okay, well, it's trans. The carbon chain is going onto the other side of the double bond, so it's a trans molecule. But it turns out cis-trans isomerism really only works for simple molecules. Here's a couple of other ones that get even more complicated. This one only has one actual carbon on the other side at all. This one has carbon chains going on all directions. This one has 3 carbon chains and then has an ether over here. So there's a whole lot that's going on here. If cis-trans isomerism is not enough, we can switch to EZ notation. And it's easy, but it's not easy. Pun right there. E stands for entgegen, which is the German word for opposite, and Z stands for zusammen, which is the German word for together. I just remember that Z means the same side. It's ending up on the same side of the molecule. And instead of describing the molecular parent chain, we use it to note the priority of the groups that we're talking about. So for the rules of priority when you're dealing with a double bond, highest priority goes to whatever has the highest atomic number. Very important. It's atomic number of all of the stuff that you're looking at. If they're tied, you just keep moving away from the double bond to the first point of difference where something has a higher priority. So, for example, going through here, we can do these kind of difficult ones. So we only have to care about the two sides of them separately. So first one we've got up here, we've got O and we've got a Cl that's directly attached to it. O has an atomic number of 8, Cl has an atomic number of 17. 17 wins, so 17 is going to be our higher priority on the left side. Then over here we've got C, which is atomic number 6, N, which is atomic number 7. 7 is a higher priority. Cl was higher, N was higher. They are on the same side, so this will be a Z configuration. Going to this one, they're all attached to a carbon, but then we have to list what things each of those sides are going to be attached to. So this carbon is attached to hydrogen, hydrogen, hydrogen. And this one is attached to carbon. That first carbon beats that first hydrogen. So carbon, carbon, and hydrogen. This one has a much higher priority than this one. And then this one over here, we've got a hydrogen, hydrogen, hydrogen. And this one here, we've got a carbon, hydrogen, hydrogen. Notice I'm listing them from highest to lowest priority of what they're attached to. So that carbon that is right there beats the fact that there are 3 hydrogens here. So this would be the priority on this side, and this would be the priority on this side. So that is going to be an E configuration, an Entkogen configuration. Finally, our little bit more complex one, this is an O. O beats C because O has an atomic number of 8. C has an atomic number of 6. And then over here, we've got carbon, carbon, and then 2 hydrogens, and then 2 hydrogens. Here we have carbon and 3 hydrogens. Here we have carbon, and that's attached to a carbon and 2 hydrogens. So this carbon here, notice that it's 1, 1. This one here is attached to 3 hydrogens. This one here is attached to 2 hydrogens and a third carbon. So that one's actually higher priority. So that means O is higher priority. This leg is higher priority. They are opposite of each other. So that is going to be an Entkogen, an E configuration. And I believe that should be what the next side is. So Cl beats O, and then N beats C. First point is a tie. On second point, the C beats the H up here. First point is a tie. Second point, C beats an H over here. O beats the C. First point is a tie. Second point is a tie. And then third point, C beats H. Okay. So Z, E, E. Now, very important to note here. And I will stare directly into the camera to make sure that you know what I'm talking about and why it's important. You cannot assume that trans configurations would be E and cis configurations would be Z. That will not always be the case. For example, in this picture right here, molecule number 3, you would probably say, well, the chain is starting here and the longer one's here. So this would be a cis configuration. They would be entering and exiting the same side, but you would be wrong. By higher priority rules, it is an E configuration, not a Z configuration. So make very clear that you are only allowed to use cis and trans as identifiers whenever you are talking about something that is just only that on each part of it has a hydrogen and then something else, a hydrogen and then something else. Because again, the other piece of this double bond would be the hydrogen that rounds out because carbon needs to have 4 bonds to stuff. So only when that's the case are you allowed to use cis and trans. Okay, I've got 3 examples, and then I've got 3 pictures as well. They're getting a little bit complex now that we're getting later in here. I'm going to do those examples, though, in a video for next week. All I want to work on is just some very basic identifying cis and trans or drawing cis, trans, EZ configuration molecules for this week. That's all I've got for this video. This is Mr. Diamond signing off. Let me know if you guys got any questions.